Okay, so we are back again. So next we will take another example, right? Second example. So in this case, you have to calculate the node voltages in the circuit shown in figure 3.4a, right? So it is your what you call, in this circuit you have to find out V1, V2 and V3. Before moving to the problem, first let me mark it. This is your node 1. This you have to find out V1. This is your node 2, you have to find out V2, and this is your node 3, you have to find out V3, right? And you have in this circuit, you have one independent current source, that is this one, this 3 ampere current source, that is independent current source, and one dependent current source is here. This is your 2 Ix, right? And Ix is here, right? And you have to we have to find out that V1, V2, V3, the node voltages V1, V2 and V3. So let me clean it first, right? So let us move to this or what you call that problem. So in this case, now that figure 3.4b shows the circuit analysis for the figure. Now this circuit is redrawn. This circuit actually is redrawn, and this is your voltage V1, I told you, this is voltage V2 and this is voltage V3, and currents are marked in different your what you call node. So this is node 1, this is node 2 and this is node 3, right? So for example, further I mean before moving to that solution, how we will do it? For example, here you have to apply your what you call KCL. So if you apply KCL, suppose at node 1, this is your node 1, if you apply KCL, then this 3 ampere current, this is independent current source, this 3 ampere current is entering into this node, right? Therefore you can write, and the other two current, that Ix and I1 is leaving your node 1. Therefore this one equation is 3 is equal to your I1 plus Ix, right? So this is your what you call that your I1 plus Ix. Now if you take the direction of I1, the direction of I1 is like this. This current, this I1 actually flowing like this. This is like this. Here it is I1, right? Therefore I1 is equal to, it will be your V1 minus this, those voltage is V3. So minus V3 divided by this resistance is 4. So this is your I1, right? Similarly, your I2 is equal to Ix is equal to, this Ix is equal to, is moving from node 1 to node 2, you have to see the direction. So Ix equal to your, it will be V1 minus V2 divided by this 2 ohm resistance divided by 2, right? So this is your expression for, because it is a nodal analysis, so you have to apply KCL and then you find out your what you call I1 and I2. That means this equation actually it will be V1, I mean if you put I1 is equal to V1 minus V3 by 4 plus Ix V1 minus V2 by 2 is equal to 3. That means this equation will come like this. It is I1 is equal to your V1 minus V3 by 4, right, plus your V1 minus V2 by 2 is equal to 3, right. So this will be your, if you apply KCL, then this will be the your what you call that equation in terms of voltage V1, V2, V3. That is your in equation 1, right. Similarly, if you apply your what you call that KCL at node 2, so let me clear it, right. So similarly, if you apply KCL here at node 2, then Ix is your what you call incoming current is Ix, right, incoming current is Ix, and your that and other two current I2 and I3 are leaving that node 2. So it is actually I2 plus I3, right. So similar way, your Ix is equal to, you can write V1 minus V2 by 2, this is Ix, is equal to your I2, right. I2 will be is equal to V2 minus V3 divided by 8, because this resistance is 8 ohm, right. This is I2, and I3 your plus that I3 will be is equal to V2 minus 0 divided by your 4, because this is 4 ohm, right, and this is your reference node. So here reference voltage V0 is equal to 0. So V2 minus 0 by 4. So this way you can apply your what you call that your KCL at node 2, right. Later I will come to the solution, but just for the purpose of explanation, let us try to your what you call explain this. Now next you apply KCL at node 3. So first let me clean it, then I will write. So second case, this case you apply your what you call KCL at node 3. In this case, this I1 plus I2 is equal to, because this current is entering, I2 also entering at a node 3, and 2Ix current is a dependent current source, it is leaving the terminal. So at node 3 if you apply, so it will be your I1 plus I2 is equal to your 2Ix, right, because this apply KCL, that is your what you call KCL at node 3. So I1 is equal to your I1 is equal to, already we have seen, it is V1 minus V3 by 4, because this is 4 ohm resistance and this is voltage V1, this is voltage V3. So I1 will be equal to V1 minus V3 by 4 plus I2. So I2 is equal to your V2 minus V3 by 8. So V2 minus V3 by 8 is equal to 2 into that Ix. Ix 2 into Ix means it is 2 into, this is a dependent current, Ix is equal to your V1 minus V2 by 2, because this is Ix, Ix is equal to V1 minus V2 upon 2. So upon simplification you will get some relationship, right. So this is actually your what you call that your KCL at your KCL at node 1 we have seen, what is this, node 2 we have seen, and node 3 we have seen, right. So everywhere you will find only 3 branches. Here at node there are one branch, 2 meeting of 3 branch actually, right, but according to the direction of the current we have applied KCL. Here also 3 branches, here also 3 branches, right. So let me clean it. So whatever I have shown, right, now this at node 1 we are writing this equation. Here one error is there, that is your at 3 here it is, just hold on, right. This is 3, this 3 was missed, right. So it will be V1 I1, I told you V1 minus V3 by 4 plus V1 minus V2 by 2. If you apply the same thing, it is actually 3. Here actually I have missed is equal to, right. So this is a correction. Now then upon simplification you will get 3 V1 minus 2 V2 minus V3 is equal to 12. This is your equation 1, right. So next at node 2. At node 2 I told you Ix is equal to I2 plus I3, right. So let me clear it. So at node 2 I told you, this is at node 2 your what you call Ix is equal to I2 plus I3, that I have written the equation also for you. So here also same thing. So at this is your Ix is equal to V1 minus V2 upon 2. This is V1 minus V2 upon 2, this is equal to I2 V2 minus V3 upon 8 plus V2 minus 0.4. So upon simplification it is minus 4 V1 plus 7 V2 minus V3 is equal to 0. So this is equation 2. Similarly at node 3 also I have showed you how to write equation. So same thing I am writing, that I1 plus I2 is equal to 2Ix. All these things I have rewritten before, right, before coming to this. So here also upon simplification you get 2 V1 minus 3 V2 plus V3 is equal to 0. This is equation 3. Now to use Cramer's rule we put equation 1, 2 and 3 in the matrix form. Let us solve it using Cramer's rule, right. So let me clean it. So this is equation 3 and other 2 equations 1 and 2 already given. So let us clear it, right. So next if you put the matrix form, the equation is coming like this, that is your this is your A matrix, this is your A matrix, right, it is 3 into 3 matrix, and this is your X means it is your state variable V, voltage V, V1, V2, V3, that is your X, and this is your B matrix, your n into 1, that is your B matrix n into 1, right. So basically it is a column vector. So 12 0 0. So based on that, suppose that next is your solution for this one. V1 is equal to at the time of your explanation of Cramer's rule, the solution of there we wrote no x1 is equal to delta 1 by delta, x2 is equal to delta 2 by delta till xn is equal to your delta n by delta. So in this case your x is nothing but your V. So, here it is V1, V2 and V3. So, V1 is delta 1 by delta, V2 is equal to delta 2 by delta and V3 is equal to delta 3 by delta, right. So, we have to obtain delta 1, delta 2, delta 3 as well as delta, the determinant of this matrix, right. So, let me clear it. So, in this case what we do, that 3 into 3, this rule, this delta is equal to this rule, I told you this is true only. Remember, this is this rule, whatever we have made it here for computing the determinant, it is true only for 3 into 3 matrix, only for 3 into 3, no, for no other matrix you cannot do this. This is only for 3 into 3 matrix. That is why if you have a 3 into 3 matrix, rather than finding out cofactor other thing, directly you can get the determinant quite easily. So, let me clear it. So, in this case, that 3 minus 2 1, first you write down the matrix, that 3 minus 2 minus 1, then minus 4 7 minus 1, then 2 minus 3 and 1. After that you repeat the first two rows, that is first two rows, this is this first row you repeat, the 3 minus 2 minus 1, then second row you repeat minus 4 7 minus 1, minus 4 7 minus 1, this you repeat. Next, this all these things make algebraic sum, right. So, it is 3, then how we will directly have calculating, that first one is, look, 3 into 7 into 1, right. So, this will have a plus sign before that. So, it is a plus, right. So, it is a plus sign. Next, your put plus sign like this, then you make it like this, that minus 4, right, then minus 3, then minus 1, right. This is your but plus sign, but all elements should be taken, whatever signs they have, minus 4 into minus 3 into minus 1. Next is this one also, say plus, so it will be 2, right, then minus 2, then your what to call this minus 1, right. So, 3 into 7 into 1, so this part is 21, so here it is 21, right. Then it is minus 4 into minus 3 into minus 1, so it will be minus 12, so that is why it is minus 12 plus minus minus, so minus 12. Then this one 2 into minus 2 into minus 1, so it will be plus 4, so this is plus 4. So, this part is done, the right hand side is done, right. So, next you will come to the this side, this will be negative. So, I am putting somewhere here, look, it is minus, right. Then this side, if you come like this, then minus in 2 into 7 into minus 1. So, 2 into 7 into minus 1. So, if you multiply this, it will be actually plus 14, this will be actually plus 14, I mean this one when you multiply this one, right. So, that is why it is plus 14, right. Next, you multiply this one, your what you call minus sign will be there. So, minus sign, then it is minus 4, right, then it is minus 2, then it is 1, then it is 1. So, it will be actually minus 8, right. So, this is here I am writing, this is actually your what you call that your minus 8, right. Sorry, this is not minus 8, this is the third row, sorry, this is the just 1 minute, just let me clear it, I have missed that third, I have written the third term, it will be this thing, just hold on. And second term is this one, this will be minus, so it is your 3 into minus 3 into your minus 3 into minus 1, right. So, 3 into minus 3 into minus 1. So, it will be actually minus 9, right. So, that is why it is minus 9 is here, right, minus 9 is here. So, next is your this term minus 4 into 2, I mean next is this term. So, it is minus, then minus 4 minus 2 into 1. So, it will become minus 8. So, that is why it is minus 8, right. So, previously when I was explaining, I was overlooked this thing, right. So, that is why this determinant is 10 using this rule. So, it is very easy to compute, just repeat and just you take this algebraic sum plus and this side should be, this is all minus, left hand side and right hand side all plus. So, it is very easy rather than finding out, only true for 3 into 3 matrix. So, let me clear it, right. So, with this delta we got 10. Similarly, your find out delta 1, delta 2 and your this thing. So, in that case, for finding out your delta 1, that if you look into this, that first row is replaced by that B matrix. B is 12 0 0, right. So, first row is replaced, first column is replaced by 12 0 0. So, if you look into the previous matrix, only this column is replaced by 12 0 0, right. So, and this is minus 2 7 as you do, and similarly following the same thing, you repeat these two rows, here at the end, and this 12 minus 2 minus 1, 0 7 minus 1 and 0 minus 3 1, all are there, but repeating the first two rows here, and following the same thing, you find out what is the value of delta 1, right. So, let me clear it. So, if you do so, delta 1 you will get, this is actually 48, right. So, here it is here it is your delta 1 is equal to 48. Similarly, for delta 2 also, that second row second column of that matrix you replace by 12 0 0. So, if you look into that, this is the second column is replaced, 3 minus 1 minus 4 minus 1 2 1 all are there, only second column is replaced by 12 0 0. Earlier for Cramer's rule it has been explained, right, only second row you second column you replace. So, and following the same thing you compute, then you will get delta 2 is equal to your 24. So, delta 2 is equal to 24. All these things for the DC circuit we are trying to understand for DC circuit, all these things in detail. Same philosophy will be applied for AC circuit, single phase AC circuit as well as 3 phase AC circuits. At that time I need not explain all these things, because by that time we will go through everything. So, it will be easier for me, and at that time consumption will be less compared to present one. So, each and everything we are trying to understand, right. So, this is delta 2, so is equal to 24. So, clean it. So, right, similarly delta 3 also in similar way you compute. So, that is delta that you call last column of the 3 into 3 matrix you replace by this rest of the elements of a matrix will remain same, right, and follow the and repeat the first two rows here. So, first two rows repeated, 3 minus 2 12 and minus 4 7 0, that is all these things repeated, and follow the same thing for computing delta 3, and you will get delta 3 is equal to minus 24, right. So, once you got then what we can do it now, you know that let me clear it. So, V 1 will be delta 1 by delta, and so V 1 is equal to delta 1 by delta. So, it will be your 48 by 10, so 4.8 volt. V 2 will be delta 2 by delta, so answer will be 2.4 volt, and V 3 will be your minus 24 by 10 delta 3 by delta, so minus 2.4 volt. So, this is the solution, right. So, this is a simple one, I mean how to solve it, but this rule what for computing determinants, actually it is true for 3 into 3 matrix, right. So, let me clear it. Now, then nodal analysis, next we come to the many more examples we will see nodal analysis with voltage sources, right. So, now we will now consider how voltage sources affect nodal analysis. For the purpose of explanation, consider figure 3.5. So, suppose as soon as nodal analysis with voltage sources, so just for the purpose of this thing, let us this circuit we initially have taken. Now, question is that here little bit let us try to understand that one reference node is there, right. This is at reference node voltage V 0 is equal to 0, right, and you have it is a nodal analysis. If you look into this circuit, right, these are non-reference node, this is V 1, this is V 2 and this is V 3. So, node 1, node 2, node 3, these are non-reference node, right. Now, before coming to this super node concept, before coming here, that this is the nodal voltage V 1 and it a 10 volt source is connected here, that means that this datum node or reference node voltage is 0. So, basically here V 1 actually is equal to 10 volt, right, because this is the only voltage source connected here, right. So, this is actually called, this is actually V 1 itself will be 10 volt, because whatever is there from this non-reference node to your datum node or reference node, that 10 volt source is already connected. So, V 1 will be equal to 10 volt, this you have to understand. Second thing is that if any voltage source is there between two non-reference node, So, this is one non-reference node and this is another non-reference node. In between, if you have any voltage source, like here we have a voltage source say 5 volt, then this combination is creating a super node, we call super node, right. And in the super node, both KCL and KVL you can apply, you have to apply, right. So, just to for understanding, if any voltage source is there between two non-reference node, then that will be super node. That means this whole thing together is a super node, right. And in this case you need KCL and KVL both. Now, question is, if this combination itself is a super node, then how you can apply KCL? So, in that case what you have to do is, so this is the current I1, this current I1 entering into the super node, up to this you will come, right. This whole thing is a super node, I have marked it here, it is a super node, right. So, this current I1 is entering here, right. Similarly, if you look into that, this I4 current also entering into the super node, right. So, this is another thing, and other thing is that current I3 is leaving the super node and current I2 leaving the super node, because you have to at that time we are not considering like this node or this node, as a whole it is actually super node, right. So, you have to see in this, that means how to remember that if any voltage source is connected between two non-reference node, that actually combination it creates a super node, right. And in that case you have to see that this current I1 is entering into this your super node and current I4 also entering the super node, because this is as a whole, right, as a whole this dashed line whatever I have given, it is a super node, and current I3 also leaving the super node and current I2 also leaving the super node. So, in that case that I1 plus I4, these are the incoming current to the super node, and I3 and I2 leaving the super node. So, is equal to I3 plus your I2, because these two are leaving the super node. So, this is what you call both KCL and KVL, both you have to apply. So, first KCL. So, when we apply KCL to super node, so this equation is coming, right. I hope you have understood this, the concept of super node. So, now let me clear it. So, that is why this dash line it is there, it is creating super node. So, current I1 is coming here entering into the super node and we entering into the dash region, right. I4 also and I3 and I2, these two are leaving. So, this is actually you have to consider as a super node. Now, whatever I said that V1 I told you 10 volt, whatever I tap is there, that is a different thing, that already told, and this is your what you call I1 plus I4 is equal to I2 plus I3. This is your super node that KCL when you make it. Now, in next if you try to write down all this I1, I2, I3, I4. So, I1 is equal to, is as simple as before, I1 is equal to your what you call that V1 minus V2 by 2, right, because this is V1, this is V2, this voltage is V2, this is V1. So, I1 is equal to V1 minus V2 by 2, right. Similarly, your I4 is equal to V1, this resistance is 4 ohm, V1 and this is V3. So, it will be V1 minus V3 by 4, right, that is your I4, and I3 is equal to this I3 writing here, I3 is equal to this is V3 and this is reference node, its voltage is 0. So, basically V3 minus 0 by 6. So, V3 minus 0 by 6, this is your I3, and similarly your I2, this I2 is equal to this voltage is V2, the reference node voltage is 0. So, V2 minus 0 by 8, this is your I2. So, that means your I1 plus I4 is equal to I2 plus I3, replace those I's by all V voltages V1, V2, V3, then you will get one equation using KCL. So, that is why this is clear, I am clear, let me clear it, right. That is why this equation we are writing V1 minus V2 by 2 plus V1 minus V3 by 4 is equal to V2 minus 0 by 8 plus V3 minus 0 by 6. So, right. So, this is next in the super node you have to apply KVL, right, one KCL, because you have to whenever a super node is there, a constraint equation will come, right, whenever a super node is there, a constraint equation will come. So, how to make it? Look, I will make it like this, explanation is there later. So, question is that I have to apply your what you call that I have to apply your KVL also. So, forget about the circuit, only this point as it is V3. So, suppose this is for your understanding, suppose this is my your what you call node 3 and this is my node 2, right, and in between the voltage source is there minus plus, right, and this voltage is 5 volt. So, this is and this is connected and here voltage is V3, this is the reference node. So, basically this is actually ground, this is actually your actually it is ground. So, this voltage is V3. So, this is plus, this is minus, and similarly here also this voltage, this node 2, right, it is actually voltage is V2, this is plus, this is minus. That means this V3 is actually that what you call the V3, it is the voltage across this, right. So, basically V3 will be is equal to 6 into I3, right. Similarly, here also your V2 will be actually 8 into I2 from Ohm's law, right. So, rather than that means this rather than in this circuit we will take the total voltage V3. So, this is V3, this is plus minus, right, this is plus minus, right. Now, what you do in the clockwise, you apply KVL in this equation, because super node requires KCL and KVL both, because of this voltage source one constant equation will come. So, if you move like this, so it will be look minus 5 because it is encountering minus 5 voltage, because this is minus sign, right, plus this voltage is V2. So, plus V2 encountering plus sign first, then here it is encountering minus sign first, minus V3 is equal to 0, right. That means that V2 minus V3 is equal to 5. This is the constant equation coming because of the super node. I hope you have understood this, right. So, whenever super node comes, you make this circuit and make it clear such that things will be totally clear. This is actually node 3, this is actually node 2, and anything whenever I make symbol like this, arrow like this. So, arrow means it is always plus and nothing is mentioned means it is minus, right. So, any super any non-reference node to take, this should be plus sign, this should be plus sign, this should be plus sign, and this reference one should be minus 1, right. There should not be any confusion. So, the V2 minus V3 will be 5. So, let me clear this, right. Therefore, this equation, this is the same thing is redrawn here, this same thing is redrawn here, plus minus, this only clockwise we are moving applying KVL whatever, and this is the dash line shows the other component of circuit, but our interest is only this much whatever I showed, right. So, if you do so, you get that same equation V2 minus V3 is equal to 5 whatever just now whatever we wrote, V2 minus V3 is equal to 5, right. So, let me clear it. So, then equation 19, it is chapter 3, that is why 3.19, 3.1, 3.22. So, equation your 19, your just hold on, equation 19, 21 and 22, this 19 this 19, 21 and 22, we obtain the node voltages. Therefore, a super node has the following properties. Number 1, a super node requires the application of both KCL and KVL, that I told. A super node has no voltage of its own, right. Super node has no voltage because 2 node and 1 voltage source, all these things are combination is making a super node. So, super node has no voltage source of its own, and the voltage source inside the super node, voltage source provides a constant equation needed to solve for the node voltages, right. That means your, let me clear that what is that constant equation, this one, this V2 minus V3 is 5, this is constant equation coming because of that super node, just I told you, right. Therefore, your what you call that it needed to solve for the node voltages, right. So, thank you very much, we will be back again.